Now, let us do one of very nice inequalities in statistics, which is called the Cauchy-Schwarz inequalities. You have an analogous mathematical inequality, which is Cauchy-Schwarz inequality, and there is a relationship between the two inequalities. So, let x y be a bivariate random vector, then provided the involved expectations are finite, expected value of x y whole square is less than or equal to expected value of x square into expected value of y square. The equality is attained if and only if probability y is equal to c x is 1 or probability x equal to c y is 1 for some real constant c. So, that means you will have equality if and only if y and x are kind of linearly related. Second part says that expected value of x is mu x, expected value of y is mu y, variance of x is sigma x square, variance of y is sigma y square, and all are finite. Then correlation between x and y will always be between -1 to 1. So, what it says is correlation has to be always between -1 to 1 for any random variables x and y, and this would be derived using the Cauchy-Schwarz inequality. Not only that, it says correlation is plus minus y if and only if x minus mu x upon sigma x is plus minus times y minus mu y upon sigma y with probability 1. So, that means correlation square is 1 if and only if x and y are linearly related. This is what it says. So, in some sense this correlation can be used to verify in certain situations whether x and y have a high linear relationship or not. So, if correlation between them turns out to be 1, that gives a impression that x and y may be linearly related. So, there is some kind of a relationship between x and y probabilistically. So, let us consider the following two cases. First case is expected value of x square is equal to 0. Now, I know that if expected value of x square is 0, then probability x equal to 0 is 1. If probability x equal to 0 is 1, then probability x y is equal to 0 is also 1. So, it follows that then expected value of x y would be nothing but 0 times probability of 0 times 1, which is 0, expected value of x would be 0 times 1, which is 0. So, in this case probability x equal to c y is 1 for c is equal to 0 because x is 0. So, we have a equality in the Cauchy-Schwarz inequality, which is expected value of x y whole square is less than or equal to expected value of x square into expected value of y square. This is what this inequality said. So, here expected value of x square is also 0, expected value of y square is also 0, because x is 0 with probability 1. So, both the sides you get equality, and in this case you know that x is same as c y for c is equal to 0 with probability 1. Now, let us consider the situation where expected value of x square is positive. Now, let us look at this quantity y minus lambda x whole square, where lambda is some real constant. So, these are expected value of a positive quantity, and I know that expected value of a positive quantity or a non-negative quantity is always non-negative. So, these always greater than or equal to 0. Now, I expand this becomes y square minus 2 lambda y x plus lambda square x square, and expectation being linear, this becomes lambda square expected value of x square minus 2 lambda expected value of x y plus expected value of y square. So, this is always greater than or equal to 0 for every lambda. So, what I get is lambda square expected value of x square minus 2 lambda x y plus expected value of y square is always greater than or equal to 0, whatever the lambda may be. So, this suggests that the discriminant of the quadratic equation lambda square expected value of x square minus 2 lambda x y plus expected value of y square is equal to 0 has to be non-negative, and that gives me 4 times expected value of x y whole square is less than or equal to 4 times expected value of x square to expected value of y square. So, this is a lambda square plus b lambda plus c is equal to 0. So, discriminant. So, this is greater than or equal to 0 if and only if b square minus 4 a c is less than or equal to 0. So, that is what is over here, that is discriminant is always less than or equal to 0. Sorry, this note should not be 4, this should be 2 b square. So, 2 expected value of x y is the b. So, 2. So, now this 2 4 because 2 square is 4, that gets cancelled with this, and you get the Cauchy-Schwarz inequality. And certainly, in the Cauchy-Schwarz inequality, I will have a equality if there is a root of that quadratic equation. So, that means x equal to y minus c x whole square is 0 for some c belonging to R. But that happens if and only y probability that y minus c x is 0 with probability 1, or probability that y is equal to c x is 1 for some c belonging to R. Now, to see that how the fact that correlation between -1 to 1 follows from the Cauchy-Schwarz inequality, I may consider the random variable z1, which is x minus mu x upon sigma x, and z2, which is y minus mu y by sigma y. Then expected value of z1 would be nothing but expected value of x minus mu x upon sigma x. So, expected value of z1 would be 0. By the same logic, expected value of z2 would be 0, because mu x is a mean of x and mu y is a mean of y. Variance of z1 is nothing but variance of x minus mu x by sigma x, which is same as variance of x minus mu x by sigma x square, because you know that variance of a times x is same as a square variance of x. But variance of x minus mu x is same as variance of x, because variance of x plus constant is same as variance of x divided by sigma x square. So, you get sigma x square by sigma x square, which is 1. So, variance of z1, which is equal to z1 square, is 1. By the same logic, variance of z2, which is equal to z2 square, is 1. So, variance of z1 is same as variance of z2, which is same as 1. And what is expected value of z1 z2? This is expected value of x minus mu x by sigma x multiplied by y minus mu y by sigma y. Sigma x, sigma y being constant, they can be taken outside, and it becomes expected value of x minus mu x, y minus mu y by sigma x, sigma y. But this quantity is nothing but covariance between x and y. Expected value of x minus its expectation, y minus its expectation, and then you are taking the whole expectation, which is the covariance x y, divided by this is a square root of variance of x, this is a square root of variance of y. So, this gives me rho of x y. Now, I use the Cauchy-Schwarz inequality, which says expected value z1 z2 whole square is less than or equal to expected value z1 square equal to z2 square. But expected value z1 z2 is nothing but rho of x y. So, rho x y whole square is less than or equal to 1, which is equivalent to saying that rho x y is always between -1 to 1. And I will have a equality if and only if probability that z1 is equal to c z2 is 1 by the last result, which is part A of this result, for some c belonging to R, which is equivalent to saying that probability that x minus mu x by sigma x is same as c times y minus mu y by sigma y with probability 1 for some c belonging to R. But since variance of x minus mu x upon sigma x is same as variance of y minus mu y by sigma y, which is 1. So, if this probability is 1, so variance of this should be same as c times variance of this. So, you get variance of x minus mu x by sigma x, because probability that this random variable is same as this with probability 1. So, this is same as probability that y c times y minus mu y by sigma y, but that is same as c square variance of y minus mu y by sigma y. But this is 1, this is 1. So, this gives me c square as 1. So, very interesting thing that correlation in some sense can be used to see if x and y are linearly related or not. If, for example, rho and x y is suddenly clear near 1, that would say that x and y are linearly related. But if it is far away from 0, that does not mean that they may not be linearly related. They may still be linearly related. Same time, if x and y are correlation between x and y is 0, I cannot conclude anything about their relationship. Now, let me give this as a take home problem. So, let x y be a bivariate discrete random variable with probability mass function given by this. Here p I belonging to 0 1 and 2 p 1 plus 2 p 2 is 1. So, that this is a proper probability mass function. Find the correlation between x and y. Are x and y independent? So, you will see that correlation between x and y turns out to be 0, but x and y are not independent in this case. In fact, if you see over here, correlation is 0, but if you see the relationship between x and y is same as x square with probability 1. So, these are example where correlation is 0, but there is a perfect quadratic relationship between y and x. So, take this as a take home problem. Now, before I conclude, let me give a summary of the next module. In the next module, we will discuss the concept of conditional expectation of absolutely continuous random variables. So, that was all for this module. Thank you for patience and have a great day.